This video demonstrates parallel to serial data conversion using AT89S52 microcontroller programmed in assembly language. The assembly code used in this project uses conditional branch instructions. We'll start with the jump on 0 and jump on no 0 instruction. This part is the opcode and this part is the operand, which is a label. So a jump on 0 label means jump to label when the accumulator is 0. Jump on no 0 label means jump to label when the accumulator is non-zero. The next branch instruction is the jump on carry and jump on no carry instruction. Jump on carry label means jump to label when the carry flag is 1. Jump on no carry label means jump to label when the carry flag is 0. The next instruction is decrement jump no 0. So the register content is decremented by 1, and if it's non-zero, then the program will jump to the label. The next instruction is jump on bit and jump on no bit instruction. Jump on bit works by checking the bit value. If it is 1, it will jump to the label. Jump on no bit, on the other hand, will check the bit value. If it is 0, it will jump to label. The bit here is basically a port pin, such as P1.0. The assembly code also uses logic instructions, and we'll start with rotate left through carry, which means rotate the content of the accumulator left by 1 through the carry flag. And rotate right through carry means rotate the accumulator content right by 1 through the carry flag. This diagram demonstrates the rotation right through carry instruction. So this is the accumulator before the instruction is executed. It has a byte where D0 is the least significant bit and D7 is the most significant bit. And the carry flag would have a value of either 1 or 0. Now after executing the instruction, D0 will be shifted into the carry flag and the content of the carry flag will be shifted into position of the most significant bit, and D7 will shift into this position and D6 will shift into this position, and so on. Also, as part of the logic instructions, we have the set bit instruction where the operand bit is set to 1. And the operand bit can either be a port pin or it could be the carry flag. Also we have the clear bit, which means set the operand bit to 0. A block diagram of the implemented system is shown here. The objective of this system is to convert the input 8-bit parallel data into serial output. And this is done by storing the 8-bit data inside the accumulator and then shifting it out either least significant bit first or the most significant bit first. The output is indicated by these two LEDs. If the output is 1, red LED will be on. If the output is 0, blue LED will be on. And the buzzer will trigger every time there is an output. And this is the circuit diagram of the implemented system. We have an 8-bit dip switch connected to port 0. We have two push buttons connected to port P1.0 and P1.1. And we have the buzzer connected to port 3.0, and we have the two LEDs connected to port 3.2 and 3.5. And now for a quick demonstration. First we press the least significant bit button. Now we press the most significant bit button. A quick look at the assembly code. We set ports P0 and P1 as input ports, and we set port 3 as output port. We turn off the buzzer and we set up a counter with an initial value of 8. Next we get the input byte from port P0 and store it in the accumulator. And then we check the status of the two push buttons. If no button is pressed, then we jump to start and the loop continues. If we press the least significant bit first button, then the program will jump to this label. At this subroutine, the first thing we do is to rotate the contents of the accumulator right through carry in order to examine the least significant bit of the accumulator. Then we store a copy of the accumulator into register B, and then we put a 0 into A, and then we check the carry flag. If the carry flag is 0, the program will jump to label logic 0. If the carry flag is 1, then the program will jump to label logic 1. Next, we get back from register B the contents of A, and then we decrement the counter R3 by 1, and then we check. If it is non-zero, then it will jump to this label, and we have a loop that will loop 8 times. After the loop finishes, the program will then jump back to the main routine. When we press the most significant bit first button, the program will jump to this subroutine. Here we will rotate the contents of the accumulator left through the carry in order to examine the most significant bit of the accumulator. We store the contents of A into register B, and then we put 1 into A, and then we check the carry flag. If the carry flag is 0, the program will jump to logic 0. If the carry flag is 1, the program will jump to logic 1. Then we regain the contents of A from register B, and then we decrement the counter by 1 and check if it is 0 or not. If non-zero, it will jump to this label, and we have a loop that will loop 8 times. After the loop, the program will jump back to the main routine. Within the subroutine least significant bit first, if the carry flag is 0, which means that the bit that was shifted from the accumulator into the carry flag has a value of 0, the program will jump to this label logic 0. Inside subroutine logic 0, we turn on the blue LED and we turn on the buzzer, and then we apply some delay. And then we turn off the LED, and then we turn off the buzzer, and then apply some delay. Next, we check the contents of the accumulator, and don't forget, back in the least significant bit first subroutine, we put a 0 in the accumulator, so this jump on 0 will be executed, and the program will jump to again 1, which is here, back inside the least significant bit first subroutine. Back inside the subroutine least significant bit first, if the carry flag is set, this means that the least significant bit of the accumulator that was shifted into the carry flag is at logic 1, and the program will jump to this label logic 1. Inside subroutine logic 1, we turn on the red LED and the buzzer. We apply some delay, and then we turn off the LED and the buzzer, and then apply some delay. And then we check the value of the accumulator. If the accumulator has a value of 0, then the program will jump to this label again 1. Otherwise, if the accumulator has a non-zero value, the program will jump to label again 2. In a future video, serial data communication will be established between two AT89S52 microcontrollers, where one will be the transmitter and the other will be the receiver. Thank you for watching.